First is our basic question, and this is talking about the estimates of daily intakes of calcium for 38 women between the ages of 18 and 24. And they give us our amounts right there, and then it asks us to display a histogram. So here's my histogram. I did the amount of people in each range on the bottom and then going up, so it kind of tells you that between 900 and 1100 are the most, and that's around 8 people, and then kind of like looks like 7 and 5 in that range of people are in the rest of them. So then our first real question is the mean, the standard deviation, and the standard error. So what I did was I just put it in my calculator in the list 1, and I did 1 var stats, and I found my mean, my standard deviation, and then my standard error. I did a neat little formula which included the standard deviation and etc. So then we find the 95% confidence interval, and this I did PANTS, so the parameter is the daily intake of calcium. Then we assume normality based on central limit theorem, because there's 38 people and that's more than 30, so you assume your normality. And then independence and SRS are also assumed. So it's a one sample t-test, and this would be our basic formula, but instead of the z it would be a t. And then this is what I got. You put your mean, your t-score that you get from your t-score table, and then your standard deviation, and square root the n, or the amount of subjects that you have. And then this is the range you get because you have to do the plus and the minus. So this is the minimum and this is the maximum. And then here's my statement that we are 95% confident that the daily calcium intake is between the interval of 786.378 and 1065.674. Asks us to eliminate the 2 largest values and recompute the 95% confidence interval. And what did I notice? Well, these are the 2 largest numbers, so I just took those out, and then I redid the list 1 and list 2, and I got our new mean, which is a little lower. It's 856.194 new standard deviation, and then our new n, which is 36, because we took out those 2 numbers. And it's the same test. It's a 1 sample t-test. And so here's our new formula, and then here's our new values. We got 753.264 and 959.124. And here's my statement that we are 95% confident with the 2 biggest numbers removed that the daily calcium intake would be between 653.264 and 959.124. And these values are significantly smaller than these. This one's not that much smaller, but you can tell that this one really went down, and especially the mean went down a lot too. So that's kind of what I've noticed. And this is talking about a game that we play against an opponent, and like how the probability changes whether you win or lose the first one, depending on like what you get for the second one. And then our first question is, what are the 2 games independent? And I said no, they are actually dependent on each other, because if you win the first one, the probability of you winning or losing the second one are different. So on here it says if you win the first game and then you also win the second, it's 0.2, but if you lose the first game and then you win the second, it's 0.3. So those 2 change, which makes it very dependent on each other. And then our next question is, what's the probability that you would lose both games? And then this is kind of tricky because you have to do 1 minus 0.4, which is the probability that you would win the first game is 0.4, so you're trying to find what it would be if you lost, so that'd be 0.6. And then the same thing for this, it's 1 minus 0.3, because if we lose the first one, the probability that you would win the second is 0.3. So you do 1 minus 0.3, which is 0.7. Then you times those two together and you get 0.42, which is your probability that you would lose both games. Then the third question is, what's the probability that you would win both games? And this is kind of easy because it says the probability that you'd win the first game is this, and then if you win that game, the probability that you would also win the second is this. So you just times those two together and you get 0.08. And then it asks to make a little probability model, and this is how I made mine. This is the probability, like what you would get, and then this is the actual like probability amount. And so we already did the win-win and lose-lose, so we put those in there. And then win-lose and lose-win are dependent on just like interpreting these and then plugging them in and doing that. So if you add them all up, it equals 1. So I made a little pie chart to kind of make it a lot easier for people to look at. Obviously, win-lose and lose-lose are bigger than lose-win and win-win, because they're going to make it hard to win both times, so it's just natural. And then it asks for the expected value and the standard deviation. So I did those two formulas. This just asks to times the 0, 1, 2 wins. So 0 wins would be 0.42. 1 win would be 0.5, because if you add those two together, it's 0.5. So that would be just 1 win. And then 2 wins would be 0.8 or 0.8. So you would plus all those together after you multiplied them together, and then you get 0.66. And then standard deviation kind of works the exact same way, it's just a lot longer. I had to go kind of down on the page, but you end up getting 0.62.
Of the day is the AP question, and this is talking about comparing two methods determining the level of E. coli bacteria in beef. It gives you method A and B, but these are matched pairs, so you end up putting the difference in your calculator. So I just did the difference right here, and then I inputted this into a list, and then I did the var stats, and I got our mean, our standard deviation, our n, which is 10, and then our degrees of freedom, which is 9, which is just 10 or n minus 1. So I did phantoms for this problem because it just asks to give evidence on kind of like which method is better, are the methods the same, are they different, etc. So the perimeter is the level of the E. coli in the beef and the difference between the two methods. And you automatically assume that the SRS is given. You assume normality with caution because there's only 10, but it seems to be pretty normal based on that it's not fluctuating that much. And then independence as well, you assume that. And here's your ho and ha. Your ho would obviously be that there's absolutely no difference between the two methods, that they're the same. And then your ha would be that they're not the same, they're completely different. So, it's a one sample t-test. Yikes, that's crooked. And this is your test, kind of like the little equation that you would use, and you just plug it in. Your standard deviation and your mean were already given, and your n. So you just plug those in, and then this is 0 because this equals 0. And then you get 1.4563, and then you go into your t table, and that gives you between 0.05 and 0.1. But since there are two different methods, you have to times it by 2. So you'd end up getting 0.1 and 0.2, like what the p would be in between. And so you do all that jazz, and you end up getting p equals 0.1792. And that's right in between those two, so that checks out. And then here's my statement. We failed to reject the ho of the two methods having the same because the p of 0.192 is lower than the alpha of 0.05, like the 5%. So that is your statement, and that is the end.